how the layout is going to be there, and so how your stick diagram depicts almost closer to the layout, and what it does show and what doesn't show. So we'll try to learn now how to draw stick diagram now. Okay, so how to draw a stick diagram. So we'll try to first analyze with a CMOS inverter. So how we can draw the stick diagram. So you already remember the circuit of the CMOS inverter, right? So here we go. So first thing is we'll draw a VDD line and ground line. So later part, so we're going to draw the demarcation line next, and the next thing is we need two transistors here. One is PMOS transistor and another one is NMOS transistors. As discussed, I told you all these PMOS transistors should come above this demarcation line, and all the NMOS should come below the demarcation line. So I'm going to draw the P substrate to make P transistor here, and N substrate here. So in the stick diagram we found the rule, that is rule 1, something like rule 3 I think, right? So whenever a diffusion is crossed by polysilicon, that means transistor is formed. So I need to draw perpendicularly to polysilicon layer. So before that I just made a contact here, because this is one P substrate material is a metal layer. So there are two different layers. So since those two are connected, so I made indicate the contact here. And this is the polysilicon right side, right, like perpendicular to diffusion regions. So this is one transistor here, and this is another transistor. Okay, so this will be one terminal. So in this case this will be source of the PMOS, this will be drain of the PMOS. So this will be drain of the NMOS, and this will be source of the NMOS. So in the circuits we know that, so these two things are connected. The gate of the PMOS and gate of the NMOS are shorted together, and this drain and drain of these two things are shorted and taken as an output. So the next thing is we're going to connect this one, and you can see I'm using a metal line. This is a blue color, because we understood that only two layers can cross this demarcation line. So one thing is polysilicon line, another one is metal layer. Okay, so the substrate, these two things cannot cross each other. Okay, that's why I'm using metal layer here. So this metal, I'm going to indicate the contact, because these two are different layers. And next thing is we going to go for polysilicon connections. Okay, so this is how your stick diagram looks for a CMOS inverter. And there is some another way of indication of the same stick diagram. So this is another way of representation, the same stick diagram, and there is some differences here. So you can see from the first one, when you compare to the second one, this we can say it's something like more optimized. So why I'm saying so means, so you can see the wire length what we are using here. So for in this structure of polysilicon, the length is more, right? The more polysilicon is used here. Okay, when you go for routing purpose. Okay, so when you compare to this, so it's going to use more. So here a less polysilicon is used, right? So why means in the polysilicon layer is the high resistive, highly resistive layer. So you know that we're going to study in the next upcoming topics. So when resistance is more, obviously it's going to contribute for the delay. Okay, so the delay will be increased. So you need to minimize the delay. So you should optimize the stick diagrams so as to the layout to reduce the consumption of polysilicon. Okay, as much as possible. Okay, right. So this is another way of representation. You can either go with this one or you can go with this one. Right, so we have similar circuit here, an example. So this is for a NOR gate. So this is your NOR gate structure. So we have A and B, that is nothing but NOR means A plus B whole bar. Okay, so for this particular circuit, so I will show you how we can draw these circuits. So in the further in few minutes. Okay, so I'm going to show you how to draw the uh, circuit. So for time being, so you can see this is the NOR gate, and corresponding layout, sorry, stick diagram should look like this. Okay, so this will be our substrate material. Okay, so this is one transistor, this is another transistor here. So So this is one transistor, another transistor. So this will be A, this will be B. Okay, and similarly this will be again A and B. So all these are interconnected. You can just look through it, go through it. Okay, right. So similarly, so when you go for the next stage, so this is for a function f equals AB plus C whole bar. Okay, AB plus C whole bar. So this will be a circuit for it, and there is another way of writing similar circuit. The C can come down, A and B can go up. This is also the correct circuit, and this will be your stack diagram for that. Okay, right. So when you quietly observing the two circuits from inverter to then the previous NOR gate circuit and this one AB plus C. If you keep on writing the stick diagram in this fashion, so it's quite looks complicated, right? So since it is having color code, it's fine, but when you're writing, try to write in a monochrome, it will be quite difficult, right? This will be quite difficult, and you're using so much of different layers here, right? It is not an optimized one, and when you have only three variables here, so then only you are getting some complications here, right, to write the stick diagram. So similarly, what we will do, so we will go for a technique called Euler's method. So where you are writing a Euler's graph for your circuit, and you are going to identify the Euler's path for it. So then you are going to draw the stick diagram. Okay. So this is also correct way. So if somebody has given an examinations, if you give this equation, you can write stick diagram in this fashion also. So no issues with it. Okay. So they have to give you marks, but so it's better if you depict the stick diagram in terms of Euler's method. Okay, so getting the Euler's path and then writing the stick diagram. Okay, right. So before going to that, I will try to uh, go for different thing. uh, right. Okay, so first thing is, so I need to tell you what is how you're going to write the circuit. Okay, for any uh, equations, right? So how do you write a CMOS circuit? So first thing is, whenever you find something like for NMOS, if you find something like A star B, okay, so uh, then for PMOS, so you connect in uh, parallel, okay, and for NMOS transistors, so connect in series. You need to remember this, so to write. And sorry, I think yes. So okay, you can just remove this one. So when you are find A star B, so PMOS transistor should be connected in parallel, and NMOS should be in series. And similarly, if you go for A plus B, okay, something like A plus B, so then the same thing. So PMOS should be in series connection, and NMOS should be in parallel. Okay. Okay, so you need to keep remembering these 2 points. So you should remember this. So while writing your circuit, okay, right. So now, so when you go for any general structure, okay, so any general structure, you can find the general structure for any CMOS circuit will be something like this. So one thing is you'll have the VDD line, and so you will have a network we call as so this will be your pull-up network. Okay, this will be your pull-up network, and similarly, so you can go with another network called as pull-down network. So this will be so pull-down network. Okay, this will be pull-down network, and as usual, this will be in ground, and here you're going to take your output. So this will be your output. Okay, Right. So this will be general structure for your any CMOS circuits. You will have a network of PMOS devices, and you will have a network of NMOS devices for pull down. So PMOS devices for pull up, and NMOS devices for pull down network. Okay. Right. So we will take some example. So how to write? We'll try to write for say a AND gate. So we'll take y equals a star b or something like this. Okay. And we can also find, so we always indicate something like this bar. So y equals ab whole bar. This is your NAND gate. Okay, so I'll come to know, explain you how to write only for AND gate later part. Okay, for time being, so we have an expression y is equal to ab whole bar. So this is nothing but your NAND gate, right? So how to write a NAND circuit, right? So I can just follow this particular things. Okay, so ab a plus b. So since we have two variables here, so we need two transistors. So first transistor is a and b, and I need to make pull up network and pull down network also, right? So the structure will be like this. So first thing is I will try to write uh, so like this. So this will be one thing. Okay, so I will take this one. Okay, right. So this will be your VDD, and this will be a ground. Okay, so I need to write pull up network here. I need to write pull down network here. Okay, right. So pull up network will be of PMOS, right? So for that, when you have A star B, so what is the connection for PMOS? I need to connect in parallel. So for AB, I need two transistor. So one transistor will be something like this. Okay, so this will be a PMOS circuit. One transistor PMOS, another transistor. Okay, this is another PMOS device. Okay, so this will be, say, called as a. So you are giving input to your gate terminals. Okay, the input will be towards from the gate. So this will be A input and this will be B input, and these are connected in parallel because it is A dot B. So if it is A plus B, then you have to connect in series. So this should be connected to VDD. Both should be connected to VDD, right? This pull-up network will be connected to VDD, right? You can join these together, then you connect to VDD. That also fine, no problem with that. So this will be your pull-up network, and we need to write pull-down network. For full pull-down network, so A star B means NMOS should be connected in series. So two transistor NMOS should be in series connection. Okay, so this will be one transistor, and this will be another transistor. Okay, right. So this will be A, and this will be B. Okay, and this is your pull down network now, and here it is connected to ground. We can join to ground terminal here, and this is connected to output, right? So this is connected to output, and here also pull up network is connected to output, so we can join this. So this will be your output Y. Okay, so this is how you write the circuit diagram. Okay, so we'll see much complicated things in the examples. Further example, this is an example how to write it. Right, how to write a stick diagram now. So to write the stick diagram, so I will try to go for the Euler's path. Okay, for this only. Okay, later I will go for another example. Right, so here the first thing is, say this is the but your VDD, right? So this will be your so VDD, and this will be your VSS or ground, whatever you can write both. Okay, so first thing is I like to try to write Euler's graph for pull-up network and I will try to write Euler's graph for pull-down network. So Euler's graph, it comes in the mathematics, it's graph theory. Okay, so I'll try to write Euler's graph first. Okay, so we'll take this. So I will try to write so graph from this particular node VDD to Y. Okay, so this is my say VDD point, and this is my say Y point. Okay, say this is nothing but so VDD. Okay, and this is nothing but my Y point, and I need to draw the graph how it goes. So from VDD to Y, this node to this node, so the different paths available are, so from VDD I can go from through A and I can reach Y. So I can write this from VDD through A I can reach Y. So this edge represents the path of the transistor A. Okay, you can write this is A. Okay, so from VDD through B, so we have can reach Y. So you can write, so from VDD through Y, so this will be my B. Okay, this is my B, right? So this is one for pull-up network. This is for pull-up network graph, Euler's path. So similarly, I can write for pull-down network. So in this case, this is my pull-down network. So I can write from Y to VSS. So can take one node as Y. This is my Y node, and another node is so VSS. Okay, right. So from Y, I can have only one path. So through A, through B, I can reach VSS. No other paths exist here. So from Y, I can go from through A and through B. Okay, so this is through A and this is through B. Okay, so it's through B. So Euler's path here, Euler's path means, so you should cover all the nodes and all the edges. Only thing is, so you should go in a once. Okay, once you travel through these edges, you cannot travel back on the same edge again. Okay, but you should cover all the nodes. Okay, so you can see, so I can go from so here, so from VDD. Okay, so from VDD I can go through A. I'm not raising my hand, I'm just don't you can just trace like don't remove your pen on the paper. Okay, so start from VDD, you cover all the vertices. Okay, and without tracing back on any previously covered edges. Okay, so through VDD, so through A I came to Y, and I can again trace back through B. Okay, right? So my path I got here is A through B. So A and B. So AB is my path, and similarly I can have another path also. So from VDD I can go through B and I can go through A to reach VDD again. So I can have another path here BA. So here, so we have two networks are there, so and two graphs are available for us. So whatever the path you take, say I am taking A B, the same AB should holds good for this particular graph also. Okay, so in this case it will holds good. I will take another examples in the next stages. So here we will take through A through B. Okay, it's possible. So you have something like A B, the path. Okay, so this AB path from AB and AB satisfies Euler's method, Euler's path. So we can satisfies in both network, pull up and pull down network. So we'll consider this as a Euler's path to draw the circuit. Okay, so BA is also possible, so that's also Euler's path in this case. Okay, right. How to write trick diagram for this using this Euler's path? So you just take the very first thing is you just to go for it, two layers. So I will take Okay, this is my VDD, and I will have this is my VSS. First draw these two lines. This is my VDD line, this is my ground line. So I'm indicating using blue color because it's a metal layer. Okay, so next thing is I will indicate demarcation line. Okay, so you can draw demarcation line in a dotted Y, right? This will be my demarcation line. This is how you write it. Got it? So now I will indicate here P substrate. I'll indicate here N substrate. Okay, so for that I will try to use P substrate, this orange color. Okay, so I will try to go with this. Okay, so okay, I will just go with this with small thickness. Okay, so right. Okay, so this is my say PMOS substrate, and I will go for green color for N substrate here. Okay, right. Okay, orange, white, and green. So it looks like India map, Indian flag. Okay, let it be. Okay, so now once you draw this P substrate like this, and this will be your N substrate like this. Okay, so now I'm going to draw the polysilicon. So I will indicate red for writing the polysilicon. So since I'm using here two transistors, I need two polysilicon lines here. Okay, so one for A, another for B. So you slightly draw from here vertically, perpendicularly like this to your substrate material. This is one A, and you will have another one like this. Okay, so this will be your A, and this will be B. Okay, right. So this order will be yours Euler's path. If you get AB here, you start from AB here. Okay, so if you get BA here, so write BA here. Okay, if you have some multiple other type of say A, B, C, D, four options are available. If your Euler's path is ABCD, so you should write four polysilicon lines and should write ABCD. If you have something like CBDA, so as Euler's path, you should mention here C, B, D, A. So this is the order where I'm going to use your Euler's path, what you have got right now. Okay, right? If you just mention the wrong path here, so there'll be some issues while connecting here that you can understand while doing yourself. Okay, right. So now, so once you got this structure for the diagram, now we need to go for interconnections. So for interconnections, so my method is, so I will try to concentrate first for PMOS device, this one. I will look for this region and I will try to make connection. So how to make connections? In this pull-up network, I will look for say this region, connection into VDD first. Then I will check for the connection for the output. So then I will search for any intermediate connections left. So this is the order I go. So it will be easier and you will not forget anything while writing stick diagram. So just go through first region. Okay. So any connections from here for VDD and any connections for output and any intermediate connections. Okay. Right. So first we'll go for connections for VDD. So what are the connections for VDD here? Okay. What are the connections for VDD here? So for VDD connections, I have one terminal of A is connected to VDD, one terminal of B is connected to VDD. Okay, so you can search here in your, so you can see here, this is how I told you when you have diffusion is crossed over by polysilicon, that means a transistor is formed. So in this case, this is P diffusion. There are two transistors here, this transistor, B transistor and A transistor. So in these two transistors, one terminal is open for A and one terminal is open for B, and another two terminals of A and B are joined together. Okay, right? So they are already interconnected. Okay, so they are not available individually, right? In this case, so A is connected to one terminal, A is connected to VDD, one terminal B is connected to VDD. So here you can check it out in this network whether A and B are individually available. Yes, A is available individually, B is available individually. So you can try to connect them individually to VDD. Or so there's another possibility here. If you can also take A and B join together and you can connect to VDD. That's also the correct way, right? So both are correct way to do it. So I can choose any either of them. So here I will take say uh, one terminal of A. So you just take this one terminal of A connection. I'm taking connection now. Is connected to VDD. So I've done this. So this connection is over, and one terminal of B is connected to VDD. So one terminal of B is available here. So you take this connection and you connect to VDD, right? So this part is over. Then I'll come for this part. I said before. So here A and B together connected to Y, or A individually, B individually can be connected to Y. So you can see A and B already available together. So A and B together available like this. So you take connection from here, and where you should go? You should go to output Y. So you take this and I will connect to this as a output, say Y. Okay, right. So now, so any intermediate connections? So there is no intermediate connections because we have only two transistors. You should see that one in the next examples for higher more variables. So I'll come to the pull down network. Similar to this, I will just go here. So I will just check for this connection for VSS first. Then I will check for connections for output, and I will check for any intermediate connections. So come for this VSS part. So here the B is connected to VSS. Okay. And one more thing. So this can be interchangeable. Okay. So here this can be B and this can be A. It's also correct. Okay. It's not a wrong way. So you can this can be interchanged. No problem with that. So in that case, for your circuit, you'll get different stick diagrams, and for some other person who has written A and B like me is going to get another stick diagram. So nothing to worry about it. Okay, so here in my circuit what I have drawn, so the one terminal of B is connected to VSS. You check for any B terminal available. So this is one transistor, this is another transistor. So one terminal of B is available here. You take this terminal here, one terminal of B is connected to VSS, you join to VSS. Okay, and similarly, so one for in the come for this Y connection here, so one terminal of A is connected to Y. So one terminal of A is this one. This is A, right? It's completely A. This is completely B. Okay. So one terminal of Y is available. So you take this and you try to connect to output Y, right? So Y line is available. You try to just join them. Okay. So any intermediate connections here? So there is no intermediate connections here, right? Okay. Right. So this is how you can write. So and when you are writing stick diagram, make sure that uh, so no other endings interconnections are left back. Okay, right? So you can think of so these two terminals as two hands. Okay, so A is one person, B is one person. Okay, so one these two person held together one hands, and other hand is free. Okay, so no hand should be free. Okay, once you complete your stick diagram. Okay, that means you're leaving some connections. Okay, make sure that no terminal is uh, open. Okay, so this is how you draw a simple uh, stick diagram for your simple circuit as NAND gate. And why I'm writing is A star B whole bar, right? So I'm writing circuit for A star B using this method, that is PMOS parallel MOS series. Okay, but my Y I'm getting is A dot B whole bar. So you should remember, so this is a CMOS circuit. CMOS circuit means complementary metal oxide semiconductor, right? So whatever circuit you design using PMOS and NMOS, okay, the whatever the output you're going to get, so the result will always be complement of the input combinations, whatever circuit you're going to get. So that's why you get inverter means you have one PMOS, one NMOS, you get one input A, right? So if you give A, you're going to get A bar, right? Similarly, the arrangements whatever you're going to do here using your transistors in this fashion, using these combinations, you're going to get the complement of that particular structure. Okay, that's why, so we have A star B. If you design, so you will have, you're going to get A B whole bar. That means this is your NAND circuit. Okay, so how about your AND gate? So if you want to write AND gate, so then, so Y is equal to AB is your AND gate. So for that, Y is equal to AB. So you need to realize something like you go for double bar, and you should realize that one. So we'll just discuss that one in the further slide. I have that. We'll discuss that one. How do we write that? Okay. So this is about your how to draw Euler's graph and draw the stick diagram for it. And you can see you are not keeping this connection, right? So you can see here A and B are joined together, right? It's already joined together, so you don't need to make anything, any connections from your side. Okay, right? This is nothing but intermediate connections you have to check. Okay, right? And you can observe here I am crossing here metal lines over the polysilicon, right? Right, so these two are different layers. Even though if I'm crossing here, there is no connection, electrical contact here. Okay, these are two different layers. Okay, so here this is substrate layer, I'm using metal, I'm indicating the contact because these two are different layer, there is a contact present there. Okay, right, so we'll just go back to your slide. Right, you can draw for y is equal to ab plus c also. So we shall try for this ab plus c, so that's you can understand faster. So then I will go on the slides very fast. Okay, okay, ab plus c, right? So how do we get this circuit, right? Okay, let me finish this, then I will just go for it. Okay, so for ab plus c, just mentioned this is how you're going to get the stick diagram. Fine, and this is taken by my notes itself. Okay, so you can see this is the schematic of your transmission gate. So we are discussing the module 1, right? Right, one PMOS transistor, one NMOS transistor. Okay, connected in parallel, you're going to apply A here, Y here. This is schematic. So if they are going to ask you stick diagram for this, so for these type of things, don't go for your path, that just go for the earlier method. So this is one transistor. So write the transistor has the one P substrate. This is polysilicon. So N substrate, polysilicon. Two transistors are ready with you. So for this gate terminal, this is input is S bar. Write S bar here. And for this gate terminal, input is S. So write S here. Okay. And here connections. So this and this two are shorted. So short them using some metal line. Okay. So I'm indicating X mark here because of different layers. And similarly this one. So you just make it as A. This make it as Y as an output. So just as simple here. And you can write for the same thing for multiplexer 2:1. So usually they will ask for this particular thing in your exams for it, the schematic and stick diagram for multiplexer, transmission gate, so like that. And this is you are using the same multiplexer using CMOS technologies. You are using only NMOS here. So just replace this NMOS structure with transmission gate, so you'll get your CMOS thing. Okay, right. So this is your what we done right now to input NAND gate. This is what we realized right now in that paint. Okay, so here, so in my all examples you could see the user's path is repeated like this. Okay, so this is also the correct way. I'm just overlapping the uh, different pull up network path and pull down network path. Okay, so there I just wrote separately, so it's also correct. And here I have used to overlap. You can just follow whichever is, you just can just follow that earlier one only, no problem with that. You can just, I can just show you how this is done. Okay, so one thing is VDD to Z, I've taken output as Z. So through A, so from VDD through A to Z, and from VDD through B to Z. So from VDD through B to Z, so these edges are A and B. So now what I will write, so I will look for this my circuit. So for Z, which is nearer, so for Z A is near. So where is A? Here is A. So I will put Z here in this side. Okay, rather than putting Z here, that will become some
mistakes. Okay, so here I'll write Z. So A is near to Z. So wherever A is there, from there you are going to put node Z. Other side you'll put VSS. So from Z to VSS, so you'll just cut through. Okay. So from Z through A through B, right? So this is my A is my edge here. This is B edge. So from Z through A, I am cutting this edge. Okay, through A and through B, it's going to reach the VSS. Okay. So finding Euler's path again. So from A, I'll just go another example, right? Okay. So the same thing example that I have done before in the paint, the same thing. Okay. Right. So this is a stick diagram for two-way selector with enable. Okay. So this is one thing. You can just see. For this, I have not used any Euler's path for this. I just written as usual. This is one A transistor. This is A bar transistor. So just applying the polysilicon like that. Okay. Right, this is for NMOS shift register. So this is transistor depicted here, and so here for this depletion mode I have shown like this. Okay, so this is my depletion mode transistor. This box represent your depletion part. Okay, channel present. Okay, and you can see the ratios here. Okay, I have just depleted ratio here, but it doesn't show right here. Right, this is for NMOS shift register cell. And you'll go for another example, A into B plus C here. So this is how we write this stick diagram. So schematic first. Okay, so first thing is, so I have B plus C. I will just take B plus C. So I told you for PMOS devices, if you have plus, it connect in series. For NMOS, B plus means parallel. Sorry, oh yes, parallel. Okay, so here, so I will take this B plus C means I should write B and C in parallel. I'll just connect this one. And for entire this B plus C, A is with dot, right? A dot the entire B things, B plus C things. That means for entire this structure, A is connected with series. Okay, so this is how you write the pull down network. And for pull up network again A. Okay, so A dot means, so you need to go for writing in parallel. For NMOS it will be series, but for PMOS A dot means it is parallel. So B plus C, I will just go in series for PMOS. So A dot means this entire thing will be parallel to A. So this is how I write the circuit here. And similarly, I'll write Euler's path for this. Okay. So you can write a different way here. So this actually should come here. You can write, okay. So you can just go for, so VDD to, so whatever Z is there. So from here, so through A, so this will be my A. Okay, and through B, through C. Okay, this will be my B, and this will be my C. So, so another structure is for pull down network Z to VSS. You can take Z here, and you can take, say, okay, this is my VSS. Okay, and from Z through A through B, and from Z through A only, and through C another one. Okay, so this will be my A, and from my circuit, so this will be B, and this will be C. Okay, right. So now find the Euler's path. Okay, so for the Euler's path, we'll try to go with, so here. Okay, so first I will start with this one. Okay, so okay, I'll just take some other color. Okay, so blue. Right, so if we start with A, so from A I can go for C, I can go for B. So ACB, this is one path I got. Okay, it's working fine. The same ACB should work for pull down network also. So from A, C, B, so it's going to cover all the vertices, right? Okay, and all the nodes. Okay, so not tracing back again. So you cannot go like this. Okay, so I cannot go like A like this and again go back. Okay, it's not a proper way. So I can go with, since this ACB is going to uh, satisfy both things, so you can go for ACB as a Euler's path, just I have taken here. So the Euler's path I have taken is ACB in my case. Okay, so you can go with some other thing also. So you can also take some other uh, thing. So the thing is something like uh, okay, so you can start with say, so you can go for A, B, C. So this also covers all the nodes, right? So you can go for B also, from B, A, C. Okay, right? So if I take BAC here, so I start with this node. So BAC, I'll cover in this VDD to Z, that is pull-up network. But the same thing when you search for pull-down network, it's not going to work. See, so BAC, right? BAC. Okay. So B, okay, I can start from here and I can start from here. So if we start from here, B, so A is not available now, C is available. I cannot go back. So it's not satisfied. So if we start from here itself, okay, so B, A is available. So A, for going for C, again I should come back through A. So it is wrong one. So I cannot come. So here BAC path is not satisfying in pull down network graph. So BAC is not a Euler's path. Okay, understood? Okay, so now we can go for some other things. Say I can say something like C, B, A or A, B, C. So if you go for A, B, C, okay, so A, B and C, it's possible. A, B, C is also Euler's path. You can go for C, B, A, C, B, A. So you can hear C, okay, so you can come like this, C, B, A. This is also Euler's path. So you can go with Euler's path, any Euler's path. I have shown you how what actually is not a Euler's path. That is BAC. Okay, right. So we have taken ACB here in my stick diagram here. Okay, right. So this is the thing, and so here what I have done is, again, first thing is I have drawn a VDD line. This is how you can write in your using just a pen. Okay, so VDD line. Then I will draw VSS line first. So then I will draw demarcation line. So then I will draw P substrate and N substrate. Okay. So then I will draw three polysilicon lines because I have three variables. Okay. So three variables, three polysilicon lines. Got it? And whatever the order you are going to mention here is Euler's path ACB. If you get ABC, then you write ABC. Okay, no problem with that. So depending on your circuit diagram and Euler's path, your stick diagram is going to vary from one person to another person. Okay, so that doesn't mean it is wrong. Okay, right. So as for your taking the Euler's path in a proper way, so every stick diagram will be correct. Right. So in my circuit for this, so I have taken ACB. So first thing I told you, I will just look for this particular part. So I will look for this one. So VDD here. So for VDD, one terminal of A is connected, one terminal of B is connected. Okay. So either I should get A separately and B separately different terminals, or I should get A, B together. So these are the only possibilities. Either you will get A in separate arm as a separate arm and B as separate arm. You can connect it VDD. So if it is not available, then you should have A and B together. So in this case, in my path, A and B are together is not available, right? Because A is here, B is here, in between C is there. Okay, so A, B together is not available, but individually I have different terminals available. So A one terminal is available, so I will take this and connect to VDD, and B separate terminal is available. I will take this and connect to VDD. So this part is finished. So then I will come for this one, Z part. So another one terminal of A and one terminal of C is connected to Z. So here the same case. So A and C are individually available, or they will be available together. So in this case, individually is not available, and it is available A is already used, so I cannot reuse again. So A and C is together available. Yes. So here A and C is there. So A one terminal and C one terminals are already connected here together. So this is AC junction. So this junction. So okay. So I can take from this and I will take to the output part. Okay. So now check for any intermediate connections. So the only intermediate connection is for B and C. So this BC uh, is there, and BC is already joined together these two terminals, so there is no need to any external connection from your side. So go for the pull down network. For pull down network, so one terminal of A is connected to Z. So you can see it's available. Yes, it is available. A single terminal is available. You take this and you connect to the output line. Okay. So come to the VSS part. So B and C together is connected to VSS. B and C together is available, right? So this is CB. So the CB, BC is available. You take this BC and connect it to VSS. So this portion is done, and check for intermediate connections. So in this case, A, B and C is there. So all three terminals of A, B and C, single terminals are joined together. So in these situations, either you will find AB together or AC together or BC together. So two at a time will always be available. Okay, so you can see which one is available. So BC is there, but I already used it. So only thing available is AC. So AC is already joined together. It's available to me. So what I should do is whatever AC is there, I should take B1 terminal and join with them. That's it, right? So AC is available. So one terminal of B should come and join here. So take B1 terminal available here. You short them. Okay, short to A and C. That means this intermediate connections is over. Okay, right. So this is how you draw the stick diagram. Okay, so hope I have covered almost all the uh, things and stuff here. Okay, right. So we'll just go for another examples. I don't go through in details in the next slide. Okay, so this is for AB plus CD plus E. Similarly, I've written the structure here. Okay, so AB is there, so parallel plus CD is there, CD is parallel and E is there, so all these things are series. So you know already how I should write this circuit diagram, and just drawn Euler's graph. I just overlapped here. You can write it separately, so no problem. You just go with separate only if you get confusion with this. So I have to identify the path as CDEAB. Okay, this is my path I have already got. Okay, so in this connection, I'll just show you the connections here, how it is done. So I will see here. So A and B together. So where is A and B? So A and B together is there. It's connected to VDD. So it's done. And you come for this part. C and D together to output. Okay, C and D together is available. It is taken as output. And then intermediate connections. So A, B, and E are joined together. So either you should get AE, either you should get AB, or either you should get BE. So which is available in this case? Okay, AE is available, right? So A and E is available. I should join one terminal of B to this part so that this connection is finished. So EA is available, take that, and B one terminal is available. You take that and short them. So that becomes completes this particular connections. And you come for this here also. CE should be there, or ED should be there, or CD should be there. So you can say CD is there, but you already used it. Okay, you are taken as an output. So CD is not available for me. So either you should get CE or ED. So ED is available. Yes, ED is available here. That is DE. You take this, and one terminal of C is already available here. You can just take and short them. So this completes your P network. Similarly, I'll go for N network. Okay. So this is done. So for VSS, so we have so B, E, and D together to VSS. So in this case also we can check for either B will be available, ED will be available, or BD will be available. So anything will be available. You can in my case, so D is available. So D and E together available. I am going to connect to the VSS and have another connection. One terminal of B should be connected to VSS. It is available here. I will connect to VSS. So this part is over. So come for this part. So A, E, C together is to Z. So which one is available for me here? So A is available together. So A is available. I'll join to Z, and C single terminal to Z. So C single terminal to Z. So any intermediate connections, AB should be connected together. It's already done. No need to connect it by yourself. C and D are connected together. C and D are connected together. Okay, so this almost is the maximum complexity level you might get in your examinations. So usually till now it has not been asked in this such cases. So
If you just practice up to this much, it's more than enough. Okay, so this was that is equal to AB plus CD. So just go through it. So just anyhow I shared my notes with you people already. Okay, and this is for A into D plus C plus BC. Just go through it. If you have any doubts, try to just ping me. I'll just explain you people in the next video. Okay, if you have any doubts in this particular slides. Okay, and this is what I need to tell you in detail again. So we'll have a questions here. Realize half adder circuit in CMOS. So on stick diagram. So where inverted inputs are allowed. So this you have to take care. This will be questions will be asked. And for half order circuit, so sum will be A XOR B, carry will be AB. Okay, so A XOR B means A bar B. So I told you in the very first, so whatever the circuit you are going to realize, so in CMOS circuit will be complement of that. Okay, so that's why if I want a NAND gate, I will realize for AB. I will get AB whole bar as an output. So if I want just AB, as I said, so we need to take double bar here. Okay, this is what I have taken here. If I want to relay circuit for AB only, so I'll just go for AB double bar. So I will just go apply some De Morgan's theorem and solve this. So I'll keep one whole bar as it is. So for this one, apply De Morgan rule. So you'll get AB whole bar will be equal to A bar plus B bar. So this whole bar will be retained. So now this will be in this form. So now if I realize for A bar plus B bar the circuit, then that will be equal to A bar plus B bar whole bar. That will be again equivalent to A dot B. Okay. Right. So now for this is nothing but an AND gate, right? If you get an AND gate also, you should do like this only. So, right. So this will be your carry circuit. So A and B. So since they are said inverted inputs are allowed, so I just taken care here. So A bar, B bar, A bar, B bar. So I taken as input as inverted inputs. So similarly for AX or B, so A bar B plus A B bar. So there is no complement here. So I need a complement for writing the circuit. Otherwise, it will be something else. So I have taken double bar here and I have solved this using this De Morgan's law. Then I'm going to end up with A plus B bar into A bar plus B whole bar. So I will write circuit for this part, and I am going to get this entire circuit will be equivalent to A XOR B. So you can see this one. So the same circuit is realized here. A plus B bar. So nothing but right same thing. Okay, so A plus B bar, A bar plus B. So both are series with together, they are joined like this. Okay, so this is one, and you can see the stick diagram for that. So once you know the circuit diagrams, you know how to write this. You have taken just Euler's path and written the stick diagram for that. So this is how your stick diagram looks like. Okay, so coming to the summary part, so you understood what is stick diagram, why we need stick diagrams, and some other rules and everything, how to draw the stick diagrams. Okay, so you can try to write as a homework. So these things, okay, which already has shown you already. Okay, right. So this is it for now. So I will continue in the next session for design rules. Okay, thank you. So if you have any doubts, just comment me. So I'll be helping you out with the next video.